Dante Certification Program Level 3. In a previous module, we went over unicast and broadcast traffic. In this module, we will build on that and look at collision and broadcast domains. Many kinds of communication get onto a single wire, literally. Old IP networks used hubs or a single cable to connect computers together. This is considered a Layer 1 based network. In this kind of network, all messages are effectively broadcast messages within the network. Using a hub or a single token ring connection, we are effectively removing the sorting office from our postal system. As we saw from the encapsulation process, we can very precisely address a message. All computers therefore receive every message and have to discard anything that they are not interested in themselves. Packet switch networks use a specific IP address for IP broadcast messages that map to a specific broadcast destination MAC address. In order for this to be useful, we need something in the network to sort the mail. When talking about Layer 1 networks and broadcast messages, we have to look at the issue of network collision. A collision occurs when two or more devices send a message into a Layer 1 network simultaneously. This is not a desirable condition. When this happens, the bits being transmitted get jumbled up and there's no way for the infrastructure to separate them out. So the result of that is complete nonsense. However, there are methods for detecting collisions such as CSMA-CD, that is, Carrier Sense Multiple Access with Collision Detection. CSMA-CD works by placing a CRC block at the end of an Ethernet frame. If the CRC value is incorrect, then it is likely that a collision has occurred. In any case, a retransmission will be required to complete the data transaction. However, retransmitting the message in hopes that the collision will not occur is not very effective, especially in real-time media traffic. Another protocol, CSMA-CA, is used to avoid collisions in networks. CSMA-CA works by waiting around for a collision to happen. In the event there's a collision, it causes the sender to wait a random amount of time before retransmitting. Hopefully, each computer's random would be different, and the data would eventually be sent. Although this may work well in some situations, it does not work for time-sensitive data when sending things like clock or real-time media, like you do with Dante. CSMA-CA is used in Wi-Fi. This is why Dante is not supported on wireless networks. Now that we have talked about what network collisions are, let's see it in action. Observe what happens to the messages in this network. Here you can see a message being sent out. All devices hear the message, and one chooses to listen, while others ignore the message as it doesn't interest them. Now, two devices send out a message at the same time. Both these messages enter the network and a collision occurs. We've taken the time to understand the issue with collisions in real-time traffic. We also saw how protocols such as CSMA-CD and CSMA-CA, while being useful in other situations, are not the way to go when it comes to Dante. Having understood why that is, now let's look at how we can go about solving these collision issues. In our previous example, the network we looked at was a Layer 1 network using a hub. We identified the issue with using a Layer 1 network. So how do we solve this collision issue? It's simple. We use a switch. A switch is a Layer 2 device. Unlike a hub, it knows about MAC addresses. It has a small buffer to store and forward Ethernet frames. A switch does not flood all traffic. A switch is set to segment the collision domain. In order to do this, a switch must be able to support full-rate connections in both directions on every switch port at the same time. This is called a non-blocking architecture. In addition to this, a switch should be able to deal with contention on a single interface. This is where more than one frame needs to be sent at the same time on an interface. This means that additional backplane bandwidth is highly desirable. We saw the reason why switches are used for modern networks as opposed to hubs. We've seen how switches solve the collision issue. Now let's look at how switches segment the broadcast domain. Because every device is potentially capable of creating broadcast frames and every switch will flood broadcast frames, it's entirely possible that the amount of broadcast traffic will at some stage be significantly large enough to slow the entire network down. We saw this in action in a previous module. Just to refresh our memory, let's look at this scenario again. Pay careful attention to what's happening in this network. A broadcast message is sent. All devices hear the message. One device responds and keeps listening while the rest hear and ignore the message. Now, a second device sends a message. All devices hear it. One listens while all others ignore that message. Now, another device sends a message and the same thing happens. Then another one. Now, surely there's a better way to do this. You can see how much information that nobody is interested in is being sent around the network. Picture the amount of resources that we waste by sending messages that don't interest anyone. So, how do we deal with this? We segment the broadcast domain. As a general rule, devices should be members of the same broadcast domain if they have good reason to communicate with each other. In an audio network, it's unlikely that the mixing console would have to communicate with the office manager's computer. It would therefore be sensible to put these devices into different broadcast domains. How do we do that? We could have a completely separate wiring infrastructure and separate them onto two physical LANs. We could be more efficient and separate them onto different VLANs. By doing this, we can segment the broadcast domain. Now that we have segmented this domain, let's see what happens. You can see that we have significantly reduced the amount of wasted resources. But what if we needed to communicate occasionally within these broadcast domains? Simple. If we need two of the domains to communicate after we had segmented them, we can use a router to connect the two VLANs or LANs. Routers don't pass broadcast traffic. Routers only care about IP addresses. Routers listen for IP addresses and they look at the source and destination IP address. So the IP address information can be passed through the router while successfully blocking broadcast messages. This is also the reason why people like to break up IP subnets by function. Suppose the sales department of a company wants to be able to communicate internally but doesn't necessarily want to communicate with production all the time. In such a case, it makes sense to segment the domain to keep the sales and production departments separately. Also, segmenting in this way allows us to do filtering in the router so we can block connections if we didn't want two separate broadcast domains to communicate at all. Since this is all done at the logical layer, our wiring infrastructure can be common and we can change these settings in software and not have to go pull cables.